we've now looked at three key types of radiation that are given off to actually make a nucleus more stable. So the alpha decay involves the helium nucleus coming off. And the helium nucleus you can think of being as 2 protons then and 2 neutrons inside of those particles. Okay? And they've got a double positive charge in because of the double plus there. Now this makes them highly ionising. Okay? They're also the most massive of the radiation that comes off. So it's got more mass, it's actually got a double charge there, and it's actually moving the slowest out of the three of them. So because it's slow with a double charge, if you imagine it going past atoms then, which have got electrons in their outer shells there, obviously if they're going past slowly and they've got a double charge, there's a good chance of them attracting electrons out of those shells and therefore ionising the atoms. Okay, so that's the first part. Highly ionising because of the double charge and the slow movement there. Don't forget though, they've also got a large mass here, so the chance of them hitting an electron and knocking it out is also high. All right? You can also get this to repel certain particles away and cause ionisation. If these happen to hit molecules that are involved in chemical bonds, like in a DNA chain, it can break some of those bonds and cause damage to the genetic code there in the DNA chain. And because it is highly ionising, we also expect it to have a fairly short range in air because it will lose its kinetic energy rather quickly in the interaction with these atoms. Okay? So we're only talking about a few centimetres in air. It also doesn't penetrate very well because of this same sort of interaction, because of its size, its speed, and the fact it's got a double charge and does a lot of ionising. So it can be stopped by paper or even skin. So it won't penetrate the body, in other words, but it could give you skin cancer. So that's the first thing to realise. Alpha decay there involves a helium nucleus, which is largest, it's actually slow, double charge, highly ionising, short range in air then, and also high penetrating power. Okay? Now if you look at the other particles that are involved here, so the beta particle decay, beta plus or minus, you're talking there about positrons or electrons. Now these have obviously got less charge, because they've got a charge of +1 or -1 in this case. They've got a much, much smaller mass, about 7,000 times plus smaller mass, and they're going to go a lot faster. So these tend to still ionise them because of their charge, but not nearly as well. And they've also got a smaller mass, so they're less likely to actually interact and collide with other electrons in atoms as they go past. So they've got a greater range in air, so you're talking about many centimetres or even up to metres there, and it's going to be more penetrating than that paper one there. So the alpha particles get stopped by paper or skin, but this will actually penetrate that, and you need sort of sheets of metal of some sort to actually stop them going through, as the penetrating power is much higher. So they'll be less ionising in terms of interaction with cells in the body, and so therefore less dangerous in that regard. But I guess if you're exposed to lots of them, you're in big trouble. Okay? And it gets the inside part of the body as well. The last type there that we actually study at the moment is the gamma rays. Now gamma rays are a high energy photon, which doesn't have a mass, doesn't have a charge, and it's very fast. Now because of this, it doesn't tend to interact with the actual cells of the body as much. It has a much better range in air, okay, several kilometres, and you've got penetrating power which is much greater, so it can even pass through even sheets of lead if you like. So you need several feet of concrete or steel to actually stop these things completely if you're trying to protect a nuclear reactor core. It will actually cause ionisation if it happens to hit an electron in this situation. So if a gamma ray photon does come in and hit an electron, it will cause ionisation, but that's much rarer than the case of these others here. So it's definitely less ionising, but if you're exposed to lots of gamma rays, then you'd be in big trouble because the proportion of those actually hitting electrons and ionising and causing damage to DNA would be quite high. So we want to actually sort of avoid that gamma radiation as well. Okay, so we're saying that alpha radiation has a fairly large mass, and it's got a charge of +2, so that makes them good ionisers because they can collide and knock out electrons or even attract electrons out. The double charge obviously helps with that, and it can also cause them to repel certain particles and substances, and that also helps produce ions, by the way. Their ionising ability causes them to lose that kinetic energy very quickly, and therefore they have a range in air of only a few centimetres. They also have very weak penetrating power. Okay, so we stop by paper. So the beta minus radiation has a much smaller mass, a single charge of E minus, same with the positron by the way for beta plus decay processes. Thus they are less likely to ionise matter there, and they travel further in air, up to about a metre there roughly when you're doing those experiments. They also have a greater penetrating ability. All right? They have no mass or charge for gamma rays, and they have a low ionising power, and they go further through air. So you can think of it being like this. There's your alpha particle summary here, get stopped by paper. Beta particle rays get stopped by plastic or thin sheets of metal there, and you've got gamma rays that will get stopped by lead. Now you can get neutrons, don't forget, we haven't talked about those yet, but the neutrons have got a neutral charge, they go in quite high speed, and they've also got a small mass when you look at it, so they can actually penetrate several things. So with a reactor core, they actually tend to surround that with some thick stuff like steel and concrete to stop that stuff coming out. So you can actually detect which of these are which in some cases by using a cloud chamber or a hydrogen bubble chamber and putting some electrical magnetic fields across it to see which way they're going. That tells you the charge. So alpha particles will be deflected by electric and magnetic fields because they've got a plus charge. They've got a larger mass, so they don't curve as much. So let's have a look at these. So if you were to put in a set up an electric field here, the alpha particle source will basically sort of curve in this direction because it's got a plus charge there. Okay. The beta source is negative, so they'll curve down towards the positive plate, and you'll get more curvature on the beta source, the electrons, because they've got a smaller mass, so for the same force you'll get a greater acceleration, so they'll curve more. This one here with a larger mass, the alpha source, will curve less, and you can think of it as having more inertia, I suppose, so undergoing less acceleration and less curvature. The gamma source has got no charge, of course, so that goes straight through. Now you could get the same thing with magnetic fields. If you had a magnetic field going into the board here like that, if your positive charge goes through an alpha particle, or helium nucleus, as it goes into there, using your right hand rule then it's going to curve like that, okay, as a circular path. Not a very good circular path there. The electrons, now positrons would go the same way but be curved more because of the lower mass. Electrons would go the opposite way because they've got an opposite charge, and again they'd be circular. And of course gamma rays or neutrons would go straight through. A gamma ray would leave a finer trail in the bubble chamber, and neutrons would leave a thicker one because they've got more mass than the gammas. So you can get some indication by the thickness of the trail and also get their charge by the direction to tell which particles are which. And that applies to the other subatomic particles that you study as well. Now I've already talked about the effects on DNA and living matter. So obviously this radiation can cause damage and actually affect cell function and kill the cells or even kill people because of that. It can also cause damage to the DNA structure here if it happens to hit certain bonds there, and that DNA can then be replicated when the cells divide, and if it's a bad cell and it's dividing, you've actually basically got the cancer situation. Okay. In the exam, the key things to bear in mind here is that the ionising radiation can break chemical bonds then, therefore killing the cell, or also damaging DNA and causing cancer there. Okay. So they're the two key things to bear in mind. Now because of that, we want to minimise radiation dosages so that we don't get cancer, we don't actually get killed by radiation. You can either increase the distance to the source so you're further away from it, because a lot of it spreads out with distance, and a lot of it is actually absorbed through the air. And say alpha particles, if you're already say 30 centimetres away, you're not going to be affected by those because it's out of its range. Beta particles, if you're over a metre away, then generally you're going to be safe from them. And as you go away from gamma radiation, it's like light. The further you go away, the less you get. So twice as far away from gamma radiation, you should get about a quarter of the actual radiation there. So increasing the distance is important. So either get away from it, or you use tongs if you have to handle it, or long instruments, I guess. You can also reduce the time of exposure you get from that, so be careful not to be exposed too often with this radiation. And obviously shielding, like a lead apron, would help, or going behind some sort of a screen, because that'll absorb the radiation and protect you. Okay, thank you.